Hello, hello, hello. This is Nicholas, and I've just had a wonderful breakfast, so I figured that I would do a video before derivatives. I figured this was a good thing to add on the sandwich theorem, right? Since I just had a sandwich, I'm going to do a video on the sandwich theorem. It's really called the squeeze theorem, but calling it the sandwich theorem makes sense as well. And let me show you why. The idea of the squeeze theorem, I usually call it, is pretty intuitive. It just says, imagine you've got a graph here, and let's say, you've got this function f of x, this parabola-looking function. You've got this function g of x, and maybe you've got this wonky kind of oscillatory h of x, the weird oscillating one. And so the idea is, if we can squeeze f and g closer and closer together, infinitely close together on h, and h is sandwiched in between f and g. That's why we call it the sandwich theorem. That's where the name comes from. I think I spelled sandwich right. Anyway, I'm a math guy. I don't really care so much about English, but I think I spelled sandwich right. Wait, no. Sand, it's the H, which, sandwich. Is it sandwich? Oh my gosh, my spelling is going. Yeah, I was right. It's not sandwich. It's just sandwich. Okay. Anyway, so you can move f and g closer together, on h, and so the idea is that if we know, let's say we're looking at the point, at the origin at 0, 0, and if we know the limit as x goes to 0 of f of x, and we know the limit as x goes to 0 of g of x, and if h of x is squeezed in between f and g, in other words, it's bound between them as close as you would want them to be, or as far as you want them to be, similar to how we define the epsilon delta definition of the limit, then that implies that we would then know the limit as x goes to 0 of h of x, right? So maybe h of x is this wonky function that we don't know how to really take the limit of, but we can find two other functions that we do know how to take the limit of, that are bound in between by that bound above and below h of x, and then from there we would say that usually what you'll end up happening is that you'll get Schmajken. I'll just write Schmaj, SHW, Schmajken is less than or equal to x is less than or equal to Schmajken. Schmajken is just whatever, and you'll end up getting that the x would then have to also be Schmajken as well, right? In other words, maybe I should you'll get something like 2 is less than or equal to x is less than or equal to 2. Well, the only thing that'll fit is if x is equal to 2, and so that would tell you that the limit as x approaches 0 of h of x would have to be 2, since it's bounded above and below by 2. So a really, really famous limit, probably the most used limit, or the theorem. The reason why this theorem is used is for this limit, because this limit turns out to be very, very important. I just couldn't not do it. It's the limit as x approaches 0 of the sine of x over x. Right, we could just cancel out the x's, and we get sin. So in other words, devil horns. And we're done, right? No. Okay, so how are we actually going to do this? By the way, if it were sine of x over, say, if it were a sine of x over n, right? We could just cancel out the ends and we would get 6. Okay, no. All right. Enough. Okay, so what can we do? Well, if we plug in 0 for x, it's not going to work out, right? Because we would just get 0 over 0. So we need to massage this limit, so to say. So what am I going to do? Well, the hard part really with this squeeze theorem is coming up with f and g. In other words, you have to strategically pick them so that not only are they bounded above and below by the function sine of x over x, but also that we know how to take the limit of both of those. So sine has a geometric meaning, though, so let's consider that. So I'm going to try to draw this as best as I can. I'm a math guy, so art is not really my forte. Even with the help of this. Let's and I need to make that a little bigger because I'm going to do some stuff with this. Resize, make this pretty big. Okay, I guess that's big enough. Sine, and let's consider this to be a unit circle. So from here to here is 1. It's a radius. Now if I were to draw a triangle here, Okay, so, and let's call this angle theta here. So sine is, right, it's opposite over hypotenuse. So this length here is sine theta because it would really be, you would really be 1 times the sine of theta, but that's just sine of theta. And so this length here is the cosine of theta. The cosine of theta. Okay. Now if I were to extend this line, maybe I should just let the drawing tool do the work. Extend this line, so it's a ray. It's a ray, so it goes infinitely far in one direction. And if I were to then create another triangle I'm trying to keep this very neat, to the point, this would be the point 1, 0, then this whole blue length is just 1 because that's a radius. And I were to then draw a line up to this red ray that I have made, then this length, this blue length here, turns out to, I need to remember to turn off the thing. Turns out to be the tangent of theta. Why? Well, let me tell you. Let's say we didn't know that this was the tangent of theta. Let's call it x. Then if I were to consider this whole blue triangle, the whole big blue triangle, and by the way, the blue triangle and the red triangle, or I'm sorry, the blue triangle and the black triangle are similar by angle-angle similarity. But if I were to consider the blue triangle, then what would happen is I could say from the blue triangle that the tangent of that angle, theta, would be the opposite x over the adjacent 1. And so in other words, x is the tangent of theta. So that length there, x, is the tangent of theta. All right. Now, we're almost done with the setup here. So that length there is the tangent of theta. Okay, now we know that, let me get my laser pointer out now. This length here, this sine theta, is less than, this length here is less than this arc here, which is less than this length here. So shortest, middle, and then longest lengths, respectively. So what can we say now? Well, we can say that, first of all, we should probably find the length of this arc. The length of that arc, the length of any arc is s is equal to r theta. So s is the arc length there. R is assumed to be 1, right, because it's a unit circle, so S is just theta. And that's the beauty of having a unit circle, is that your arc length is the same as your angle. So this arc length here, I'll do it in red. This arc length here in red is just theta. Okay, so now we can finally say that theta is bound, it's got to be between sine of theta and tan theta. Okay, and we are assuming this for theta being between 0 and pi over 2. Right? So now imagine with me that we were to shrink this circle down and we were to let theta approach 0, right? Because I should probably maybe change these, since I use theta now, change these x's to thetas. So we're letting theta approach 0. That's the whole point here of this limit. So we have now actually just found two functions that are that theta is bound between from 0 to pi over 2, and that's the sine of theta and the tangent of theta, both above and below respectively. So now we can divide by, see, I want this theta to look like a sine of theta over theta, because that's my original limit, so I want it to look like that. So what I can do is I can divide all sides by a sine of theta, and that'll at least get me close, because then, I don't have to flip any equality signs, because since we're assuming theta to be from 0 to pi over 2, sine of theta is going to be positive, so we're just going to be dividing by some positive number, so the inequality signs don't need to be flipped. So we have 1 is less than or equal to theta over the sine of theta, which is good because that's just theta over sine of theta to the negative 1 is just the sine of theta over theta. So we're close. We're close. And now that's going to be less than, let's see, that's going to just be 1 over cosine of theta. Okay, now actually, so we know if we were to take the limit as x goes to 0 of that and the limit as x goes to 0 of that, then hopefully we would just get 1 for this limit. And that's true, right? Well, first of all, the limit as x goes to 0 of 1, well, that's just 1, right? 1 is always 1. And the limit as x goes to 0 of 1 over the cosine of x, I should have used thetas there, but it doesn't matter, is just 1 as well, because we can just directly substitute. So we get 1 is less than or equal to theta over the sine of theta, which is less than or equal to 1. So what does that imply? That implies then that the limit as x goes to 0, we're still going to 0, of theta over the sine of theta is equal to 1. Well, you say, but we just calculated the limit of theta over sine of theta. We want sine of theta over theta. Well, remember, I think the last video, I said that if you were to take the limit as x, or I'm changing x's and theta, but as x goes to 0 of the sine, let's do theta over the sine of theta. So that's some function in terms of theta. And we raise that to the negative 1. Right? So in other words, we're taking the limit as x goes to 0 of the sine of theta over theta, because we're just reciprocating it. So, but what we can do there is we can make that equal to, we can take the whole limit and raise it to the negative 1, which is just 1 to the negative 1. That whole limit was found to be 1, which is just 1. And theta over sine of theta is sine of theta over theta when you raise it to the -1. So that whole limit tells us that 1 is the answer to the limit as x goes to 0 of the sine of x over x. I hope you were able to follow that. Is really the squeeze theorem is not used all that much. It's really only mainly used for this limit. But this limit is very important when we go to establish derivatives. Okay. There's another limit that I just have to do here, not using the squeeze theorem, but before I go into derivatives, because I'll need it for derivatives later. Okay, and that limit is the limit as x goes to 0 of 1 minus the cosine of x over x, all over x. What I can do, and a good strategy to do, is if you remember, I think it was 2 videos ago, I gave a limit with a square root in the numerator, I think, and then I multiplied by 1 in the form of the conjugate. In other words, I just, where there was a minus, if it was, I think it was t minus square root of 3t plus 4 or something in the numerator. And so I multiplied by t plus square root 3t plus 4 over the same thing. So I'm going to do that here. In other words, I'm going to multiply by 1 plus cosine of x over 1 plus cosine of x. So now I'll get the limit as x goes to 0 of, just square the first term, square the second term, 1 minus cosine squared of x over x times 1 plus cosine of x, which is limit as x goes to 0 of sine squared of x over x times 1 plus cosine of x, which we can break up into the limit as x goes to 0. Now we can break this sine squared of x into a sine of x times a sine of x. So we can make this the limit as x goes to 0 of the sine of x over x times the limit, because the limit of a product is the product of the limits, sine of x over 1 plus cosine of x. And now this limit we have established to be 1, and this limit we can just directly substitute. And so we would get 0 over 1 plus 1, or just 0. So the limit is 0. This limit here, our original limit, is 0. So those are the 2 key takeaways here from this video, that the limit as x goes to 0 of the sine of x over x is equal to 1, and that the limit as x goes to 0 of 1 minus the cosine of x over x is also equal to 1, or is equal to 0, my bad, is equal to 0. And another key takeaway, I guess, is that you should try, if you're stuck on a limit, try multiplying by the conjugate. That's usually a good strategy with square roots and trig functions. Also, one thing I would like to point out, maybe an exercise for the viewer, Trent. So this proof that I have done, that sine of theta over theta, the limit as theta goes to 0, that limit is going to be 1, is not foolproof. In fact, what I really only did is I really only proved that the limit as x approaches 0 from the right of sine of x over x is equal to 1. Why only from the right? Because I assumed this fact here, that theta was between 0 and pi over 2. In other words, theta is from the right of 0 and then going downwards to 0. We didn't start from, say, negative pi over theta being between negative pi over 2 and 0, and then going from the left of 0 down to 0. So